Look closely at a water droplet clinging to a fern. This droplet, the leaf, and the air around them are all matter, defined as anything that occupies physical space, possesses mass, and can be perceived by our senses. In nature, this matter manifests in 4 distinct states: solid, liquid, gas, and plasma. This diagram illustrates exactly how these macroscopic states are dictated by invisible internal particles. In a solid, those particles are locked tight. In a liquid, they have the spatial arrangement to slide past one another. In a gas, they are completely decentralized. We experience these physical states on a human scale every day, but their behaviors are entirely governed by microscopic elemental rules. If we catalog the entire chemical inventory of the universe, scientists have identified exactly 118 individual elements. Look at this table detailing a living cell's composition. Biology applies a specific filter. Out of 118 universal possibilities, only 25 elements actively function in biological systems. Furthermore, just 6 elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, contribute approximately 98% of the total mass. Why did biology select these exact 6 elements over every other option available on the periodic table? Understanding why life filters for these specific elements requires deconstructing the subatomic architecture governed by universal physical laws. We must bypass the macroscopic cellular environment and descend directly into the vast, nearly empty space of an atom. This table outlines the 3 subatomic building blocks. Protons possess 1 unit of positive charge, electrons 1 negative, and neutrons remain neutral. Shifting focus reveals a weight disparity. Protons and neutrons carry roughly 1 atomic unit of mass, while an electron's mass registers as 0. Because of this weight disparity, the massive protons and neutrons pack together to form a dense central nucleus, while the lightweight electrons orbit the outside at high speeds. Figure 1.2 models the resulting helium atom in 2 ways. While the fixed planetary paths in Model B are easier to visualize, Model A represents reality, depicting the fast-moving electrons as a negatively charged probabilistic cloud. The entire structure is held together by electromagnetic attraction. The positive charge of the central nucleus pulls on the negative charge of the surrounding electrons, keeping them in the vicinity. The precise balance of mass and charge inside this single atomic unit dictates the physical properties of the entire universe. The rules inside the nucleus are consistent. The count of protons, or atomic number, defines an element's chemical identity. Meanwhile, the mass number calculates the combined total of all nucleons, both protons and neutrons, which dictates the atom's overall physical weight. But that weight can fluctuate. If an atom retains its exact proton count but accumulates extra neutrons in its nucleus, it becomes an isotope. Because these extra neutrons carry no electrical charge, the atom's electron configuration remains unaffected. Consequently, isotopes behave identically in all biological and chemical reactions. However, if the nucleus accumulates too many neutrons, it becomes unstable. It spontaneously decays, emitting its excess nuclear energy as radiation, a phenomenon known as radioactivity. This is a distinct mechanical process from isobars, which are different elements that share identical mass, or isotones, which are different elements that share the same neutron count. Biologists exploit this isotopic consistency. By introducing safely decaying radioisotopes into a living organism, scientists can track complex metabolic pathways without disrupting the delicate internal chemistry of the cell. Moving outward from the dense nucleus, we enter the vast empty space where all actual chemical reactions occur. The electrons operating in this space possess distinct amounts of potential energy, determined strictly by their physical distance from the atomic nucleus. Electrons cannot float randomly. They must occupy fixed concentric levels of potential energy, known as electron shells, designated by the letters K, L, M, and N. Look at this neon atom's electronic distribution. Arranged by the 2n² formula, the inner K shell maximizes at 2 electrons, forcing the remaining 8 into the wider L shell. Absorbing energy excites electrons to a higher orbit. Losing energy makes them fall back, emitting heat. While concentric circles are useful 2D abstractions, the physical reality consists of three-dimensional orbitals, like the spherical s and dumbbell-shaped p orbitals. These represent the specific zones where an electron is mathematically present 90% of the time. The geometry of these probability zones, combined with their energy limits, restricts how any given atom can physically interact with its surrounding environment. The most critical electrons in this geometry are the valence electrons. Because they occupy the outermost shell, they alone dictate an atom's ability to lose, gain, or share chemical connections. This brings us directly back to our 6 biological elements: carbon and hydrogen, nitrogen and oxygen, phosphorus and sulfur. They all share one crucial physical advantage: small atomic radii. A small radius creates a high surface area to volume ratio. This allows the atoms to pack closely together, forming the tightest and most stable chemical bonds possible. They also provide structural versatility. Hydrogen is capable of forming 1 bond, oxygen 2, nitrogen 3, and carbon forms 4. With its 4 bonds, carbon anchors life, but silicon sits directly beneath carbon in group 14 of the periodic table, meaning it shares the same valence properties and bonding capacity. The reason biology uses carbon rather than silicon becomes clear when we test both elements in the internal aqueous environment of a living cell. Carbon bonds remain stable in liquid water, producing non-toxic gases when oxidized. Silicon oxides form rigid, solid structures, incompatible with biological systems. Carbon is the only element structurally capable of forming stable, non-toxic, complex chains while permanently submerged in liquid water. When we watch these raw, independent elements slowly colliding, we see their electron clouds physically merging to lock together into an intricate, stable biological molecule. Every subatomic part executes its role. The dense central nucleus dictates the mass and chemical identity, anchoring the element in physical space. The external probability clouds of the valence electrons dictate the potential energy, managing the physical capacity for chemical connection. The multivalency of the CHNOPS elements provides the architectural flexibility required to build enormous, complex structures like proteins and DNA. The complexity and resilience of a living organism is an emergent property of subatomic physics. This high concentration of CHNOPS elements reflects a specific set of chemical requirements for building stable, complex structures within a liquid environment. Every aspect of cellular biology is ultimately governed by the beautiful, inevitable geometry and quantum constraints of the atoms underneath.